well, I do 1D stellar evolution, binary evolution, and also hydrodynamics, 3D simulations.
So
I'm a stellar person.
Yeah, so we like stellar people. So, so after Grenoble, you moved to Brussels.
No.
You were traveling a bit.
Yeah, quite a lot. Yes.
Okay, so maybe I was okay.
I went to the Space Telescope Institute
In Baltimore. Oh.
Yeah, in Baltimore for 2 years. Then I moved to Australia. And then back to France, Montpellier in Grenoble, and then eventually went back to the States and then to Brussels.
Okay, so
it's a long journey.
See, so we try also to say, because we have also some students here, so sometimes
no, sure,
roads or
mine is very windy.
Okay, good. So we'll start in a moment.
Yeah, sure.
I'm looking this fine.
So good afternoon, everyone. Welcome to mine, and welcome to beautiful weather, and welcome to our guest, Lionel Siess, something like this, right? Who is staying at our observatory for the entire week, working with the team of Dorota Squadron. And Lionel has a very interesting road and way to getting to the point, to the Brussels, where he is right now. He went through many continents, many institutes. He's French, and he spent some time in Australia and the States and in France. And now he's in Brussels, and he's going to tell us about the formation of barium stars. So we're looking forward and
thank you.
Hope to enjoy stuff. I'm sure.
Well, awesome. Thank you. So today I will be discussing some recent work on the formation of barium stars. I should first give credit to Pavel. So you all guessed that he's a Polish student of mine, but he's doing his PhD in Brussels and he's finishing at the moment. So this is the brief outline of my talk. So I will first introduce these barium stars, what they are. They are binaries that show chemical peculiarities, but they are also puzzling, not only because of their surface abundances, but also because of their orbital properties. And I will describe the formation channels that we think lead to the formation of these systems. And then I will describe all the physics that we have implemented, because as I will show, the standard physics doesn't work. It cannot reproduce the orbital properties of this system. So we've tried to put as much physics as we could in our code to model those systems. And then, well, of course, I will present the results and give some conclusions. So what are we talking about? Well, we are talking about binaries. And what we see is, well, the primary that we see is a low mass main sequence or giant star, typical mass between 1 and 3. And they are characterized by enhancement of S-process elements, and S-process elements like barium or lanthanum. And we know those processes cannot be made in these unevolved stars. It comes later during the AGB phase, during thermal pulses and dredge-ups. You get these interesting nuclear synthesis. So those stars, they have been polluted by a companion that used to be an AGB star. And actually, there have been velocity monitoring of many of those systems. So we have the characterization of the orbit, the periods, the eccentricity. And we can also estimate the mass of the companion, which is shown here. And we see that this is fully compatible with Rydolph companion, with a peak around 0.6, 0.65. In the title, I mentioned barium stars, but the same kind of stars can be seen at different metallicities, and depending on the metallicity, they will have different names. So close to solar, those are the barium stars. If we go to 1/10 of the solar metallicity, usually these CH stars, also binaries. And if we go even lower, we have these chemically well, these carbon and metal poor stars, but the very important thing is the S. So it means that those low metallicity stars, they have enrichment in S-process elements. So they have been polluted by an AGB component, right? And those systems are interesting because, well, if we have spectra from those systems, we can determine the composition. So that gives constraint on nucleosynthesis, the S-process nucleosynthesis. And also, if we do this long-term monitoring, we can have the orbital parameters, and that gives us constraint on the binary interaction that takes place in these low mass binaries. So this is the classical formation channel. So we start with two stars, M1 is larger than M2. So M1 evolves faster, becomes a red giant. Then it burns helium, and then it enters the AGB phase. And that's the interesting phase because it is during the AGB phase that the star will produce all these S-process elements. And also at that stage, the star will develop strong winds, and part of this wind can be captured by the companion. And those winds, they and also have these S-process elements. And once the AGB envelope has been expelled, so you find the white dwarf, plus the companion which has been polluted by the material from the AGB. So this is the phase of interaction that is the least understood, and we think that it's in that phase that most of the orbital parameters are shaped. So I will focus, the physics is mostly focusing on this evolutionary stage here. And then when the companion will evolve, so it will become a barium dwarf, then the barium giant. So you can see all the different classes, the C and P. And eventually the star can the polluted star can evolve into an AGB and produce its own S-process elements. Those, they also have been observed. So what are the orbital properties of those systems? So what I'm showing here is the distribution, well, the crosses represent the distribution of main sequence binaries from a Mermillo sample of J and K giants. We see that they cover quite a big range of periods from a few tens of days to something like 30 years. And the dots show the barium giants. And we see that, well, they share the same range in periods, but the barium stars are typically lower eccentricity, and this is due to, well, the evolution and the effect of tides. Now, if we compare with all these families of chemically polluted stars, we see that they follow kind of the same trend. So at short periods, we tend to have circular systems, and when we go to longer periods, they have well, increased eccentricity. So the fact that all these stars are looking the same in this E-log-P diagram, that was when I forgot to mention, this is the eccentricity as a function of the period, indicates that maybe some common physical processes is acting to shape these stars in this diagram. So from a theoretical point of view, we've been trying to understand these kind of diagrams. And this is our standard classical understanding of binary evolution. So you start with this distribution of period for J-type giants, this kind of Gaussian distribution. And depending on the initial orbital period, well, the star potentially will start filling its Roche-Lobe, so transferring mass via Roche-Lobe overflow, either during the main sequence or during the RGB. For instance, if the initial period is between 10 and 100 days, then what is, I should say that this is for a free solar mass. The free solar mass will fill its Roche-Lobe during the RGB. And up to something like 2,000 days or 3,000 days, there will be some Roche-Lobe overflow. And if this happens, it means that we are dealing with closed binaries, so tides will be efficient. And tides, one of the effects of tides is to circularize the orbit, so that will decrease the eccentricity, make it go to zero. And for those giants, for like the RGB and the AGB stars, which have convective envelopes, mass transfer can be unstable, Roche overflow can be unstable, and lead to some common envelope evolution. And if you have common envelope evolution, that will lead to the shrinkage of the period. So these green stars here, they will move to lower eccentricity and shorter periods. So what happens for the systems that do not fill their Roche law? So we are dealing with the yellow part of the distribution. So those are only the AGB, the one that reach the largest radii. And when we see, for instance, this is Myra, we can see, well, the AGB here and the companion, and we see that there is still some matter connecting the two stars. So there is mass transfer, but it's not Roche overflow, because the period here is something like 10 to the 5 days. So it cannot be Roche overflow, but it's wind mass transfer between the two stars. And if we use the classical binary evolution in the textbooks, and if the wind of the AGB is removed isotropically and with relatively fast velocity, then that would lead to an expansion of the separation of the stars. Basically, when you remove mass, remove the gravitational glue of the system, and they move apart together. So this is what we predict using the standard theory. That the closed binaries, they will circularize and move to shorter periods because of common envelope evolution. And the long period systems, because of the mass loss from the AGB, their separation will increase. Okay, so this is what we inject in the population synthesis code. This is the blue. So we start with this Gaussian distribution, and this is what it produces. So we understand that, so well, the short period systems, they are circularized because of ties. The very short ones are the ones that go for the common envelope evolution. And the ones that were initially somewhere here, they move to longer periods, just what I explained. But when we see the observation, they do exactly, well, their best not to fit the models. We see that these chemically peculiar binaries, they all fit into this period gap, around 1,000 days or so. There's plenty of them. We cannot reproduce them. It's a long-standing problem, and it's been up for something like 30 years. So we try to see if with some new developments in the physics, we could populate that period gap that I just showed. So to do that, we are using a binary evolution code. This is a code that I wrote some years ago, that simulates the structure of the two stars and also the nucleosynthesis, plus the evolution of the orbital parameters. And if you have a binary system, if you want to follow the evolution of the separation, you have to solve that equation. And it's just the time derivative of the orbital angular momentum. But we see that there are a lot of unknowns. The first ones are these n dots, n.1 and n.2, which are the mass transfer rate or mass accretion rate onto the primary or secondary. So we need to give some prescriptions for those quantities. There is also this J.orb here, and this one we calculated by angular momentum conservation. J sigma is the angular momentum of the binary system. So it's the combination of the orbital angular momentum plus the spins of the star. Just take the time derivative and you get this. So if we want to estimate this J.orb, what we have is to estimate the torques onto the stars, J.1, J.2, but also the rate at which angular momentum is removed from the system, typically by the wind escaping the system, the binary system. So we need also prescription for that. And of course, the last term is the change in eccentricity. So we need also some prescription for that. So I will go a little bit into the physics on how we define all these quantities. When we deal with binaries, the first things that comes to your mind, maybe not everyone, but to me, is thinking of this Roche potential. So that's how we model stars, well, binary stars. So you see that the Roche potential is the combination of the gravitational potential of star 1. So this is this potential well here, star 1. The potential well of star 2, this is this one. And you have this centrifugal term here. And if we use this Roche potential, then we can estimate the mass transfer rates. And here I show, for instance, well, some equipotentials. So you have extrema of this potential. For instance, the one that goes through this point here. So that's the L1 point. And you see that there is an equipotential that goes around the two stars. So it means that all the material that is inside one of these lobes is gravitationally bound to the star. Eventually, if the star expands, it can overfill the Roche lobe and you can have mass transfer onto the potential well of the other star. And our prescription, for instance, by Ritter or Coleman-Ritter, it gives us, well, the m dots, the mass transfer rate and the mass accretion rate onto the companion. That also gives us some torques onto the star, because when you remove mass from the star, you also take from the star its specific angular momentum. But this Roche potential is based on very crude approximations, specifically that we deal with circular orbits. And when I'm talking about it's circular systems. Also stars, which it assumes that the stars are synchronized. I will show that this is not necessarily the case, especially if the star is expanding rapidly. Well, its spin velocity will be different from the orbital one. And also it assumes that the stars are point masses. And here we are dealing with AGB stars. They are fluffy, they are big, so they are not point masses. So there are complications because if you remove some of these assumptions, then you have a change in the topology of these equipotentials. So here it's just a formulation of the Roche potential if you include, for instance, the radiative pressure from the star. It's not very relevant for AGB stars, but it is for massive stars. Also, if you include the fact that stars are not rotating synchronously, you can have some modification of the Roche potential. So we see this is what is plotted here. So if you set F-rad, well, it's basically the Eddington factor, to set it to 0, then you recover the standard Roche potential with the figure of 8 is L1. But if F-rad increases, we see that the lobes, they detach. So eventually I will take this example here for F-rad is 0.6. So if the star expands beyond its Roche potential here, you see that all the mass will not be transferred, will not go systematically to the companion. It can actually escape from the system. And those deformations of the Roche potential can lead to non-conservative evolution. So we remove more mass, and eventually if you remove more mass, you may potentially make the system get tighter. This is something that we need to reproduce the observations. Another problem with Roche overflow is if you deal with a giant star, a star with a convective envelope. Maybe you remember that if you simulate a convective envelope, it's a polyslope of index 1.5, and when you remove mass, its radius increases. And the mass transfer rate is proportional to how much the star exceeds its Roche lobe. So if you remove mass, the star will expand, it will further overfill its Roche lobe, and this is a runaway situation that will lead to a very high mass transfer rate into the system. And if the companion is not able to assimilate all this mass, well, the mass will just pile up and it will fill its Roche lobe as well. And we end up in this common envelope evolution. And when we are here, there is first a loss of co-rotation, and then the companion gets immersed inside the envelope of the companion of the giants. And because of drag forces, the orbital energy will be shared to the envelope and also the angular momentum. So the companion will start to spiral in. And when it spirals, it will release its orbital energy. And that energy, if it is larger than the binding energy of the giant, you may expel the envelope. And if you expel the envelope, there is no more friction, no more drag. The binary sits as it is. That's how you form this cataclysmic variable short period system, a few hours. But if there is not enough energy, then they merge. Okay? So this is something that is also complicated, and that comes into play in the process. One of the things we have to consider also is that, well, these Barium stars, they have been polluted. So we have to account for the fact that even if you have a wind, there may be some pollution. If you have fast wind, there are some classical expressions, the Bondi oil Littleton accretion rate that you can estimate. They have seen that. This is valid when the wind velocity is fast. But AGB stars, well, they have a slow wind. And this is something that I illustrate here in this simulation. So it's a 1.5 plus 1 solar mass with high eccentricity. So you have here the AGB star that is losing mass. Well, we can't really see the arrows, but that shows the velocity field. And you have the companion that crosses the wings, so it accretes some matter. We see the formation of an accretion disk around the companion, and we see also that there is a shock. There is a two-arm shock. Well, yeah, it shows here. And it's just the fact that the orbital velocity is not constant, it interacts with itself, and it gives some very strange structures. And we see here that the interaction is much more intense. And eventually, well, you can transfer much more mass if the wind velocity is lower. And this is what is illustrated here, the impact of the parameters when we do these split simulations. So the top panel, contrast is not great, but shows the orbital plane, and the bottom shows the plane perpendicular to the orbit. And it shows the effect of the parameters. So, well, unfortunately, you can't see, but there is nothing really to see. If you have a low mass companion, this is this case, the AGB wind remains basically unperturbed. So it's spherically symmetric. In this case, it's when we increase the mass of the companion. So the mass is 0.01. Here we increase the mass of the companion, and we see this typical spiral forming. So that's the shock. And so it forms, you have the companion that orbits in the wind, that forms a shock, and in the wake of the shock, because there is still a radial component that forms this spiral. And if you look in the plane perpendicular to the orbit, we see some arcs forming, and they are just the cross sections of these spirals that you see. In this case here, I decreased the wind velocity from 20 kilometers per second, which is relatively fast, to 5. And we see a spiral as well, but barely. But the most distinct feature is the profile in the Z direction. We see this density enhancement. It's not like here it's relatively spherical. There are structures inside it, but it remains globally spherical. But here it's really flattened, and the mass tends to accumulate in the equatorial plane. So it's a mass. If you have this density, equatorial density enhancement, that means that more mass can feed the companion. Okay, and when you transfer mass, you also transfer angular momentum. So for the evolution of binary components, that's important to follow that curve. And in this case, well, we can't really see, but it's when you get even shorter separation, then the spirals, all these structures, they start to interact together, and that gets very, very complicated. So if we, yeah, okay. Another thing that is important with the wind of AGB stars is this so-called concept of wind Roche-Lobe overflow. This is something relatively new, quite new, something like 15, 20 years. And the idea is the following. So you know that AGB winds, they are dust driven. So what happens when you have, well, there are pulsators, but you have also convection that eventually lift the material to layers which are cooler in temperature. And in those cooler layers, then dust can form. And when you have the grains, the dust grains which are formed, then the radiation pressure on the grains, they push the grains, and the grains, they drive along all the gas. And this is how you eject the material of the AGB. Now, well, consider our binary system. If you have the dust formation radius, which is outside the Roche-Lobe, means that up until this dust radius, the wind is not accelerated by the radiation pressure. So it means in that configuration, the mass that is going through L1 will have a low velocity. And this is what I illustrated in the slide before. When you have low wind velocity, you have this focusing on the material on the equatorial plane. So it means that you can have a relatively efficient mass transfer onto the companion. Mass transfer also means changing the orbital parameters. Conversely, if you have if the dust formation radius is quite inside the Roche potential, then the wind is accelerated, and when it reaches L1, it has a high velocity and does not interact so much, so you accrete less, and the change in orbital angular momentum is also different. So that's the first point with this wind-Roche overflow. But also what simulations have shown, and this is here, so you have the AGB, the companion is somewhere here, so you have the mass transfer, this wind mass transfer is efficient. It's a bit like Roche overflow, but you see that you dump quite a lot of material, and actually it escapes the system from the L2 point, the Lagrangian point behind the companion. And the material tends to circularize in a disk. And those simulations, they tend to lead the formation of circumbinary disks. And as I will show later, those circumbinary disks are important ingredients in understanding the eccentricity of this system. This is the same view, but in a plane perpendicular to the orbit. We see the cross-section of the disk. This is the AGB, the companion here, and got all the outflow around. So we need to estimate this mass transfer, especially because the AGB winds have a low velocity, so we cannot just use the Bondi oil. And this is what Saladino has done during her PhD. She was doing SPH simulations, and she estimated, well, the mass accretion efficiency is beta. Beta is just a ratio of the mass accretion rate onto the companion divided by the mass loss of the primer. The dotted line that you can see here, they are the Bondi oil predictions. And we see that at high velocities, this is as a function of the wind velocity divided by the orbital velocity. So when the wind velocity is high, the simulation, the different dots are for different setups with different mass ratios. And the solid lines are fits to this point. So we see that at high velocity, the simulation agree with the theoretical predictions, but at low velocity, we see that the mass accretion rate is much higher than predicted by the Bondi oil. Also, when we do these simulations, we can estimate how much angular momentum is lost by the escaping material. Okay, and we parameterize this quantity by eta, which is related to this J dot sigma. So that's the rate at which angular momentum is lost from the system. So it's eta times the separation. Well, so basically, this is the specific orbital angular momentum and the amount of mass that leaves the system. And if we have fast winds, then we recover this so-called Jeans mode that lead to an expansion of the orbit. But we see that when the wind velocity gets slower, well, the curves, the eta parameter tends to increase, so you remove even more angular momentum, and you have orbital shrinkage. It's completely opposite effect than the classical scheme predicts. Okay, so we implemented those formulations also in the code. The last term that is missing is this E dot term. Okay, so as we've seen, well, the first component of think of change in eccentricity, the first thing that comes to your mind is the eccentricity. So the thing to remember is that there are prescriptions, there are very complicated theory about tidal interactions, but they strongly depend on the structure of the star. If the star is a convective envelope, then the efficiency of tide is much larger than if the star is a radiative envelope. Strongly also depends on the separation of the systems. R divided by A, the separation to the power 8. So if you're far away, tides will have almost no effect. And it leads to two effects. Well, synchronization, that's the Earth-Moon system, when showing always the same side, but also to the circularization of the orbit. So when we estimate the tides, that gives some torques onto the stars, and that provides us with one contribution to this E dot that we need for the evolution of the orbital parameters. But the thing is that we need to increase the eccentricity, and the tides, they will tend to circle around. So it's not what we want. But there are processes that allow the eccentricity to increase. And that happens, for instance, when you have phase-dependent mass loss or mass accretion. the simple case, when you have an elliptical orbit, when the companion goes closest to its to the primary at periastron, the star may potentially overfill its Roche-Low. Okay, but when it moves at apastron, then it detaches. So you have along the orbit different phases of detached systems. When it gets closer, well, eventually it fits Roche-Low. This is what is shown here. So 0.5, the phase 0.5 is the periastron distance, and this is the mass transfer rate, units of 10 to minus 3 solar mass. And you see this kind of Gaussian shape that depends on the parameters. And by the way, the change in these different curves is when I use these different assumptions for the Roche-Low. When I take into account, for instance, asynchronism, I have a variation in the mass transfer rate just by the deformation of the Roche-Lows. There is also the possibility, so that leads to we can derive it mathematically, that leads to a contribution, an eccentric pumping terms, the fact that mass is transferred episodically at a given point. You can also have another term when you have the wind mass loss rate that changes along the orbit. So, well, you would say, well, the mass loss is something intrinsic to the star, how the companion can change the mass loss. Well, the idea behind it is that if you have a companion, its gravitational attraction will lower the effective gravity of the mass-losing star. And so if you are at apastron, you have, well, gravity felt by the material at the surface of the star is less than if you are at apastron, and that gives a modulation of the wind, of the mass loss. So you can derive it quite right. But something new, quite new, that appears quite some time ago, but that has not been really implemented in the binary evolution code, is to take into account the formation of the circumbinary disk. As I showed, when you have wind Roche-Low overflow, you have this so much mass dumping onto the companion that part of it escapes from behind the companion, eventually circularizes around the binary, and you form the circumbinary disk. And the idea that was developed by Goldreich and Froment, but also by Martinovich and Lebeau, is that, well, you can have resonances between the binary and the disk. The particle, the epicyclic frequency at the inner rim of the circumbinary disk may be in resonance with the binary, and that can generate some eccentricity. Very complex theory, but the thing is that it depends on the surface density of the disk at the Lindblad resonance. The fact is that we don't have a value for sigma. So what we do is just to estimate it. You have a source term. So the first term here is how much we feed the disk. So you have this zeta parameter. So this is the mass that is lost from the system, let's say from the wind. And you have a fraction of it that goes into feeding the disk. And you have this term. This is just the viscous dissipation of the material in the disk. So we can follow the evolution of sigma that gives us these E dot rates. So you see that by adding these new processes, we enrich the physics. It's not only tides that will circularize the systems, but we have also the contribution from the circumbinary disk, from the wind, and from Roche-Low overflow. So now I go to the results. So I start with, I will show a canonical model. It's a 2 + 1 solar mass. And this one is with an initial period of 8,000 days. And you remember that the stars we are trying to hit are those at a period of something like 1,000 days in the period gap. So I didn't show it here, but if we had the classical evolution, the star would just move to the right, almost at almost constant eccentricity given the separation. But here, if we include this wind Roche-Low overflow, these eta and beta parameters that I showed before that result from SKO simulations, we see that we remove so much angular momentum that we have a shrinkage of the orbit. But at the same time, so as the orbit shrinks, the two stars get closer together, while tides get stronger, and eventually it leads to the circularization of the system. And the system keeps shrinking, and eventually, when they get so close that the HGB starts overfilling its Roche-Low, and we have Roche-Low overflow here. That ends the simulation. So what we did is to scan a little bit the effect of the parameters. So we computed a small grid with varying. So the dots are the initial conditions. Well, dots on square are the initial conditions. So 3 different eccentricities and 4 or 5 different initial periods. And there are 2 colors. So the red are those systems that do not undergo Roche overflow. So we see that because of winds, well, we see that what I illustrated before, the effect of tides tend to reduce the eccentricity, and the wind Roche overflow move the systems to lower separation. When we have longer periods, well, those systems, they avoid Roche overflow, but we see the square that shows the system that enter eventually into the Roche overflow. Are the orange ones. And when we change the eccentricity, if we increase the eccentricity, the system will end up with a higher eccentricity. But we still have the problem is that this is where we find our the final stage of our systems, but we need to go somewhere here. So it's not sufficient. So, well, we have some physics. So the next thing we tried is to implement the circumbinary disk. Okay, just what I described. So this is the track that I showed before, and this is the new one that includes this effect of the circumbinary disk. And you see the effect of the pumping of the disk, these resonances. So so you still have the shrinkage of the orbit. So this is the mass that is lost by the wind, this wind Roche overflow. But because of the disk, you can increase the eccentricity. Well, eventually you get close enough that tides take over, they are stronger than the either trace term, and the system starts to circularize, but it keeps also moving to shorter periods. And what is very interesting in those systems is that, so this is the green path of the track, is where Roche overflow starts. And you see that here, the star begins Roche overflow on an eccentric orbit. And then the subsequent evolution will depend on the mass ratio. If the mass of the HGB is larger than the mass of the companion, then both the period and the eccentricity will decrease, so up to this point. And here, the mass ratio reverse, and you have an increase in the period and eccentricity. So the increase in the eccentricity, that's good. That's what we want. But we don't want the stars to move to the right. We want to populate that region here, okay, that we still cannot reach. And the interesting thing here is that, well, we end up even after Roche overflow with a system that remains highly eccentric. So this is something interesting. So we played with the parameters. We computed a small grid with different initial conditions. And here, so you see that for the long period systems, with the disk, so the eccentricity increases, but we cannot reach this region. For those that suffer this eccentric Roche overflow, so those are the green tracks, they begin the Roche overflow, and then the eccentricity increases again. But we see that those systems, they go something like 3,000 days at most, mostly 4,000. We cannot go into the region that we want. There are also systems like the blue one that are so close that mass is actually overfilling also by the L2 point, and at this point we declare the system unstable. It's probably a common envelope evolution that follows. So circumbinary disk helps. They increase the eccentricity, but they cannot move our system to shorter periods. Oops. So the next thing we did is to try this tidally enhanced wind. So as I mentioned earlier, is when the companion goes close to the primary star, then its surface gravity is decreased, and you can increase the mass loss up to a factor of 15. And if you increase the mass loss, well, basically you peel off the HGB much faster, so you prevent the HGB from reaching big radii. So it means that if you have Roche overflow, it can happen at shorter periods. And the thing is that we want Roche overflow, it has to happen. We can't avoid it. But it has to happen at shorter periods, because the problem is that after Roche overflow, the period increases again. We want to avoid that. And by increasing the mass loss, we allow the AGB to remain to have a smaller maximum radius. And we see that we move the distribution that was of the system that was initially located along this solid line, we move it to this dashed line. So we progress little by little, but still not sufficient. The next thing we considered is non-conservative Roche overflow. So that only happens when you have Roche overflow. You can say that part of the material that is flowing into the potential well of the companion may just escape from the system. And if you do that, you can remove angular momentum, so make the binary tightens again. Okay, that may be something. As we've showed, if you have a deformation of this equipotential, the mass that, well, if the star is overfilling its Roche lobe, all the mass will not necessarily go into the companion. It can go away. So this is what we tried. And if we do that, we see that after Roche lobe overflow, we have this increase in eccentricity, because Roche lobe overflow generates this E dot RLOF. So we have an increase in eccentricity. But because we move a lot of angular momentum, then the tracks, they do not move to higher periods, they move almost vertically. So we improve a little bit the situation, but still we cannot reach these gaps. It's still not possible. We tried other parameters. Well, not desperate, but well, let's see what happens. We tried, for instance, changing the wind velocity. If we increase the wind velocity, then we are more like in the classical way, and you see the tribes, they move to the right. We don't decrease, so just forget it. What we tried is also change the feeding rates. If we change how much mass we feed into the disk, how that will affect the binary. The problem here is that we have a constraint. We have constraint on the mass of the circumbinary disk. So we cannot put this zeta too high, because we would find something like 0.1 or 1 solar mass in the circumbinary disk. And this is not observed. It's typically of the order of 10 to minus 2. But so we played with zeta, but it has, of course, if you decrease the surface density in the disk, you will decrease the efficiency of tides, but that will not help with the periods. What we tried here is to change the mass of the AGB, of the progenitor of the AGB, from 2 to 1.2 solar mass. And if you have a lower mass, it will reach in the AGB a smaller radius. So we may have Roche overflow at shorter periods. This is indeed the case. In those simulations, we see that we can still populate some eccentric systems around 2000 days. But still, well, we cannot reproduce those systems at very short periods. So this is a summary with comparison with observations. So the red dots are the post-AGB systems for which we have observations. The sample is incomplete. We don't have data for long period systems. The squares are the models of our simulations when we end the simulation at the tip of the AGB, but at the tip of the AGB, there are numerical instabilities, and we had to post-process those models and see what would happen, because you still have a remaining circumbinary disk that can still act as an E dot generator, and those are the stars. So those are the post-process. So we try different combinations. So this is changing the wind velocity. This is reducing this zeta parameter. This is the enhanced, tidally enhanced feed. We try also to combine both the reduced disk feeding with enhanced mass. We try all kinds of combinations, and we cannot really reproduce. Maybe the best is this one here. Yeah, this one here, where we kind of reproduce some of those systems in that case. Otherwise, we are very far off, but we still cannot reproduce the majority of the systems which have these low periods. So, well, I didn't solve this 30-year-old problem, so that gives me a job for, well, something to do in the coming years. The main conclusion is that, well, you have to take into account these new modern prescriptions for the evolution of the orbital angular momentum. particularly if you have this wind-rush overflow, we've seen that leads to shrinkage of the orbit compared to the classical picture that you can find in textbooks. If you had a disk, a circumbinary disk, it also helps. It generates some eccentricity. This is something interesting, is that we found that if you have the circumbinaries, you can trigger this Roche overflow in an eccentric orbit. It was initially thought that if you have a star that will circularize, if a star overfills its Roche lobe, it is circularized by the time it overfills its Roche lobe, and it's always circular orbit, but not necessarily. And the problem remains. We cannot explain those systems because, well, we have Roche lobe overflow. So we know that we want to get shorter periods. A very efficient way is common envelope evolution. And this is something that is critically lacking at the moment, is some simulation of this common envelope evolution when you have an eccentric orbit. Can you, if you start these hydro simulations with some eccentric system, can you in the end eject part of the mass, shrink the orbit not too much, and maintain some eccentricity? This is something, the interaction lies into that, but common envelope evolution is a very complex problem. People have been also suggested that there may be some other processes that may explain those short period eccentric systems. And typically, if you have a binary, a tertiary companion, triple systems, then you can have some quasi-Lidov effects. So if you have these two inclined orbits, you have one, typically it's hierarchical, so you have a short orbit in the center, and you have a long one, but a long period orbit in a different plane. And what you can have is a transfer between the eccentricity of the two planes of the orbit, and, well, the inclination and the eccentricity of the orbit. And that potentially could lead to these systems, but that would mean that all those systems are triple. That's okay. Another possibility that was raised recently is that we've seen that with wind-rush overflow, we can form the circumbinary disk, and the same type of Lidov-Kodai process can also operate if you have a circumbinary disk that is inclined with respect to the inner boundary, the inner binary. And so you can have an exchange, and that could be also a solution. But the problem is that how do you form this misaligned circumbinary disk in the first place? So, well, problem remains, and well, if you have a solution, I'll take it. Thank you.
Thank you. Thank you, Lionel. Do we have any questions? Yeah.
So I don't know if I understood correctly, but those highly peculiar stars are very peculiar. So it suggests that there is a mechanism that contaminates them like a lot compared to all other binary stars in the binaries. So there has to be some additional rare circumstance that makes the enrichment operation extremely efficient.
Yeah, they are peculiar because they show its process. So we know that the companion is an AGB. So we restrict the category of binary stars. Okay, so there are low and intermediate mass stars. It means that one of the stars evolved through the AGB and is now a white dwarf that is extinct. We can't see it, but we can see the motion, the orbital motion. The thing is that wind-rush overflow is quite efficient. You can transfer between 0.2 to up to 0.5 solar masses onto the companion. And that produces a substantial enrichment because there is no S process at all in the companion. And when you inject suddenly even a little bit, that will show up compared to zero.
I'm wondering if there is some selection effect, like there is a lot of stars that were contaminated, for example, but you are choosing those that are extremely peculiar because spectroscopy can see, identify it, and these are only the chosen very small subset of those that were contaminated.
No, because
there was some additional.
No, because all the stars which are contaminated, they have been shown to be in binary systems.
Yes, but I think many stars are in binaries. So
Yes, but if you have
don't have them in the sun.
if you have a lower mass companion that did not evolve yet, let's say you have a 0.8 and a 0.6, well,
It's a matter of mass ratio.
yeah, that's the evolution. You have to have a bigger one in this one, the bigger one that pollutes. But if you have, let's say, a 0.8 and a 0.6, so now you see the 0.8, but the 0.6 is still on the early main sequence. I mean, it's unevolved at all. So it hasn't processed, it hasn't polluted, it has no wind. Just yeah.
So maybe what if you would have like very similar initial binary, and one of them had some, I don't know, tertiary or something going on that evolved, and the pollution was big, and the other was like typical, and then in the spectroscope you just don't see the ones that were polluted not as much, so they are not in your sample at all. Like an observational selection.
There is an observational selection, especially with the Barium dwarfs. So it's limited to stars between 1 and 3, because if you go at 3, so you deal with A-type stars, which are usually fast rotators, there are pulsators, delta Scuti, and so on, and they may be magnetic as well. So spectroscopically speaking, we cannot determine accurate abundances. So we know that we are biased towards those higher mass stars. But as far as the low mass, well, when you deal with between 1 and 3, I think the sample is quite complete.
Okay.
Yeah, they have been monitoring those systems for more than 10 years now with the Hermes spectroscope.
So, I have a question. You said that you varied a lot of parameters to see if it can get you closer to the period gap. Are there any more variations you can still make? You know, or is it all verified and there is no physically explained variations in various parameters that you can still make to see?
The problem is that something we cannot go around is that if they go close enough, well, you will have Roche overflow. This is a strong boundary, and when you have Roche overflow, well, depending on the reaction of the star, you can have this common envelope evolution, or if it is just episodic, maybe just grazing, you do not go into this cataclysmic evolution, but there is something that is happening, and you cannot avoid that. Given the separation, and given the Roche potential, even though it's a crude estimate, it has to have some Roche overflow. And those systems at tens of years, it means that the companion was inside the EGV. So, you know, even at 100 days, it was inside. The EGV gets so large that if you assume that the period hasn't changed, well, it was engulfed at some point. So I think that's really where lies our uncertainty, is in this common envelope evolution.
For your talk, a very specific question: can we consider Sirius as a polluted star?
I think Sirius is more massive. Huh? It's
solar masses. The white dwarf was, let's say, the dwarf on the 5 solar masses star.
Yeah,
it was really big and it could really transfer mass.
And Sirius, what is its mass? Its estimated mass?
Present of masses, about 2 solar masses for the A-type star and 1 solar mass, white dwarf. So
okay, so it's yeah. The thing is that the S-process nucleosynthesis, so this barium, lanthanum, and everything, they depends on the mass of the star, and the production of these heavy elements is stronger at lower mass than at higher mass, because in higher mass stars, it's a different source of neutrons. It's not this C13 alpha N reaction, it's this neon 22 alpha N, which only occurs inside the thermal pulse. And you have also hot bottom burning that complicates the picture. So in short, the IS process is much less efficient in massive stars, in intermediate mass stars. So if there has been pollution, it will be weaker anyway.
Sorry, I think I missed some important thing. How long lasts this dance on the eccentricity period plane?
Timeline.
Yeah.
Well, during the AGB lifetime, so that depends on the mass of your AGBs, typically in million years.
Years.
Yeah.
But the fact that there is the companion, it could accelerate the AGP phase.
Yes, especially if you have these tidally enhanced winds, you can peel off the envelope much quicker. So that will shorten also. So it's a very short phase of evolution, yes. Yeah.
And just to follow up, the initial, when you started to plot the initial eccentricity and period, this is the initial at the moment of AGB, when AGB.
No, that's at the ZAPs.
Okay, so that's a zero. Okay, so this is the very initial, I mean, the system initial.
Yes.
Okay. Any more questions? Comments? Zoom concerns?
No, there is no question.
Okay, so let's thank our speaker again. Thank you. Next week, Mateusz will tell us about some extrasolar planets discoveries, right? Feel free. Thanks a lot.
Welcome.
Yeah, so I'm wondering, because there was also one of the, I'm interested in those very high eccentricity systems. So at the beginning, when you were showing the observational, like the